Good afternoon, everybody. The first part of this webinar will be an introduction to safety glass, and the second part will discuss how additional design considerations such as aesthetics can be incorporated into project specifications without compromising on safety. We'll also incorporate the findings of our latest survey on safety glass. So just a little bit about the survey. So in partnership with City Press, we commissioned Census-wide the research consultants to undertake a survey of the level of awareness and understanding of safety glass and other glass products when specifying glass. So carried out earlier this month, we surveyed 100 UK-based architects and specifiers who said they have responsibility or influence over glass specifications. So some of the key findings from this survey will be presented during the webinar, starting with this question. So we asked, which of the following glass types generally do you believe would not be classified as a safety glass in accordance with BS EN 12600? Participants were invited to select more than one answer where relevant, and the results were as follows. So approximately half of those surveyed don't believe that laminated glass has a safety glass classification. 45% responded with heat soak toughened glass. 34% chose toughened glass. 39% believe that heat strengthened glass is not considered a safety glass. So we'll bear these results in mind as we look at different glass types, beginning with annealed glass. So annealed float glass is manufactured by the float glass process, whereby molten glass floats on liquid tin to create the near perfect finish that we're used to with modern glass. After exiting the tin bath, while the glass is around about 600 degrees, it travels down the annealing layer on rollers. So annealing refers to the process during which the temperature of the glass is slowly reduced in order to minimize the internal stresses in the glass, which allows the resulting product to be later cut and processed. If you've ever been fortunate enough to tour a float glass manufacturing operation, you'll recall that the annealing layer is the longest part of the line, and it can be as much as 160 meters in length. But in terms of safety, annealed glass is not usually considered a safety glass, as when it breaks, it tends to break into large fragments, which can cause injury. As well as attempting to transform base metals into gold, alchemists of the so-called Dark Ages also search for this desirable material known as unbreakable glass, or at least one which was less fragile than ordinary glass. Early attempts included plunging red hot glass into a bath of linseed oil. These days, the methods of manufacturing toughened glass are a little bit more sophisticated and sometimes referred to toughened glass as tempered glass. And it involves heating the glass in an oven until it begins to soften and then cooling it rapidly with air. This quenching cools the glass surface quickly, but its core is much more slowly. Compressive stress develops in the surface, balanced by tension in the center. As the inner tensile layer needs to be penetrated before it can break, then this means toughened glass is several times stronger than annealed glass. In the event of the glass fracturing, it breaks into small, relatively harmless particles, which can minimize injury compared with annealed glass. This means that thermally toughened glass can be classified as a safety glass. Laminated glass reportedly originated from a laboratory accident in which a plastic-coated glass flask was dropped on the floor, which surprised people within the laboratory that it didn't break into anything other than pieces. So that was the first kind of idea behind developing laminated glass. So laminated glass consists of two or more panes of glass bonded together with a plastic material between under applied heat and pressure. When laminated glass breaks, the glass fragments tend to hold together, tend to adhere to the interlayer material. So although the glass itself might be annealed non-safety glass, on breaking, any of the sharp cutting edges are not generally exposed. And the performance of laminated glass depends largely on the type and thickness of interlayer. The most common interlayer is polyvinyl butyral, or PVB, which is often selected for its good adhesion, predictable mechanical behavior, and ease of manufacture. Due to the manner in which it breaks, laminated glass can achieve a safety glass classification. Heat soaking is an additional process that can be carried out on thermally toughened glass, involving subjecting the glass to a heat cycle for several hours. Toughened glass can be at risk of fracture from nickel sulfide inclusions in the glass. This fracture may result when a critical nickel sulfide inclusion becomes frozen in its unstable high temperature phase within the body of the toughened glass after toughening. Over time, the inclusion transforms from its high temperature phase to its stable low temperature phase. If large enough and located in a tensile zone, the expansion in volume of the inclusion can be large enough to cause the glass to break. It's almost like having an impact from a center punch within the body of the glass. The heat soaking process attempts to force any toughened glass with critical nickel sulfide inclusions to break in the oven rather than after installation. But it's important to remember that it's still possible for toughened glass that has been heat soaked to break at a later time due to a critical nickel sulfide inclusion. Heat strengthened glass is produced by a process similar to that used for toughened glass, except the quenching is not as rapid as it is for toughened glass. So the resulting glass is stronger than annealed glass, but not as strong as toughened glass. It breaks in a similar manner to annealed, so it's not usually classified as a safety glass. It's generally not used as a monolithic glass for this reason, but it is being increasingly used as one or both plies of a laminated glass. And it has a limited risk of fracture due to nickel sulfide inclusions. I can remember 30 plus years ago when I was first asked about heat strengthened glass, when it wasn't very commonly available in the UK and there were no standards to define it. A glass processor contacted me and to ask what this heat strengthened glass he'd been asked about. And after probably a rather clumsy explanation from me, there was a pause on the line, and then he came back to me and said, "Oh, do you mean badly toughened glass?" Obviously, things have moved on since then, and now we have standards for heat strengthened glass, and they're far more better defined. So returning to our survey, we asked 100 architects which of the following types of safety glass, if any, have they used on projects in the past 6 months. Again, they were encouraged to select all that they had used on projects. So the results were 39% responded that they had used laminated annealed glass, i.e. panes of annealed glass laminated together. 36% selected toughened glass, which was also the same percentage for laminated toughened glass. 34% indicated safety film glass, and 31% heat soaked toughened glass. So there appears to be, based on our survey, a widespread use of safety glass. Alongside safety considerations, the strength of glass is another important factor during specification, i.e. designing glass to resist the loads that are applied to it without breaking. Taken from EN 16612, the European standard for determination of load resistance of glass, this slide shows the characteristic bending strength of several glass types, which illustrates ranking in terms of strength. So, for example, toughened glass with a characteristic bending strength of 120 newtons per square millimeter is stronger than heat strengthened glass, which is stronger than annealed glass. To determine the design value of bending strength for load resistance calculations, in accordance with EN 16612, several factors have to be applied to these values, for example, load duration, edge factors, and surface profile. EN 12600, the European standard, which has also been adopted as a British standard, that's why it's referred to as BSEN, provides a test method and means of classification of glass under impact from a person. So the intention with this test method and classification is to try to reduce cutting and piercing injuries to the person. The pendulum body impact test method involves impacting the glass with a double tire impactor weighing 50 kilos, drop from 3 heights. Class 3 is the lowest class and corresponds to a drop height of 190 millimeters. The highest class is class 1, which is a drop height of 120 millimeters, and in between you have class 2, which corresponds to a drop height of 450 millimeters. So that's the basics of the EN 12600 classification standard. Here is the EN 12600 test in action. In this example, a laminated glass is being tested at class 2, which is the 450 millimeter drop height. And if you look at the image in the center, they're still in the center, then you can see there's a check being carried out to see if laminated glass can be classified as a safety glass. So as long as the opening doesn't allow a 76 millimeter sphere to pass through freely, then the glass is considered a safety glass. The full classification from EN 12600 comprises 3 parts. The first part refers to the highest drop height at which the glass breaks safely or doesn't break at all. The second part describes the mode of breakage of the glass. And the third part refers to the highest drop height at which the glass doesn't break, for example, in toughened glass, or breaks safely in laminated glass. The third part of the classification in particular is useful for distinguishing between thick toughened glass and thin toughened glass, which may be needed for some types of applications. In terms of the mode of breakage, type A corresponds to a breakage where numerous cracks appear, forming separate fragments with sharp edges, some of which could be large. So this is an example of mode of breakage, typically for annealed glass. Not that a manufacturer would necessarily want to declare a classification for annealed glass. And if you look at the DOPs from various glass manufacturers, for annealed glass, they tend to declare NPD or no performance determined. Type B is where numerous cracks appear, but the fragments are held together and do not separate. So an example of this type of mode of breakage would be laminated safety glass. And then finally, you've got mode of breakage C, which is when the glass disintegrates, leading to a large number of small particles that are relatively harmless. And this is a characteristic of the breakage of toughened glass. So there are 3 modes of breakage that you have to include in the classification. So let's have a look at some typical classifications. So the classification to BSEN 12600 will depend upon several factors, including the glass type and the thickness. And also it's worth pointing out that classifications may vary from one manufacturer to another. So it's always worth checking the classification with the supplier. So for toughened glass, the classification can range from 1C3, particularly for thin toughened glass, to 1C1 for thick toughened glass. The type and thickness of the interlayer in laminated glass is the primary influence on the classification. So, for example, 6.4 millimeter laminated glass, which comprises of 2 3-millimeter glasses with a 0.38 millimeter PVB interlayer, typically achieves class 2B2. Moving on to 6.8 laminated safety glass. So that's just the same as a 6.4, except you've got a thicker interlayer. This time you've got a 0.76 millimeter interlayer, and that will typically achieve class 1B1. Most of you will probably be aware that each nation of the UK is responsible for its own building regulations as we see more and more devolution. Requirements covering the use of safety glass in the UK include approved document K in England, approved document N in Wales, technical handbook section 4 in Scotland, and technical booklet V in Northern Ireland. Talking of regulations, we asked the following question in our survey. So we said, how familiar would you say you are, if at all, with the content of approved document K of the building regulations in England and Wales, and or section 4 of the technical handbooks in Scotland? So that's a question we posed. And we had 22% of architects and specifiers said they were very familiar with these regulations, and 73% responded that they were somewhat familiar. So that means a total of 95% have some familiarity with the requirements around safety glass. Or if you flip the stat upside down, then what it means is there's only 5% of architects who are not familiar with these requirements. Approved documents and technical handbooks reference BS 6262 Part 4. That's the British Standard Code of Practice for glass in and about buildings, safety related to human impact. So this standard defines critical locations where safety glass is needed. So it's in and around doors and low level glazing in general. So any glass which is in a door or door side panel, which is within 1500 millimeters of finished floor level, needs to be a safety glass. Away from a door, so more than 300 millimeters away from the door, where the risk is considered slightly lower, then it's any glass which falls within 800 millimeters of finished floor level. So if we look at this diagram, any glass which is wholly or partially blue needs to be safety glass. The yellow areas, from a regulatory point of view, don't need to be a safety glass. So, for example, the panel above the door is more than 1500 millimeters from finished floor level. So it's considered very low risk, very little chance of somebody impacting it. And the other yellow panel further away from the door is above 800 millimeters. So again, that wouldn't necessarily need to be a safety glass. Now, in a practical situation, you'd probably want the glass to be the same throughout for consistency of appearance. But from a regulatory point of view, this highlights where you need safety glass and where you don't. So you'll find that information in BS 6262 Part 4. An understanding of the impact safety classifications for glass and an appreciation of the post-breakage characteristics can help to inform a risk assessment carried out on a specific project. There are other factors to consider or may need to be taken account, such as the strength, the location, temperature, maintenance, refurbishment considerations, and there are several others. Now, there's guidance available that's been published in the past on undertaking risk assessment for glass, particularly when it's installed at height. So, for example, CIRIA, the Construction Industry Research and Information Association, and the Institution of Structural Engineers have all produced guidance in the past. This one on the slide was actually issued a few years ago by the Flat Glass Manufacturers Association. So there's plenty of guidance and advice over there if you need to undertake a risk assessment. So at this point, I'd like to hand over to my colleague Lee, who will take you through considerations of other than safety, but without compromising safety.
Thank you very much for that, Phil. So I'm going to be looking at designing for safety and aesthetics. So glass design has evolved quickly over the last few decades, and whether the application is domestic or commercial, there seems to be a growing demand for glazing to be bigger. For example, a person may want to bring as much natural daylight into their home and enjoy unobstructed views of their garden and beyond. By comparison then, a retailer may wish to display their products in a showroom window without any glare or emphasis on the glass itself, in a bid to tempt the consumer to enter the premises. So while domestic properties face the challenges of meeting the parts of the building regulations, such as Part L for energy conservation and Part O for overheating, both of which can play a significant role in the aesthetics of a window, glazing, on the other hand, for commercial applications such as retail and zoo enclosures, don't tend to follow the same stringent energy requirements. So these applications tend to focus more on aesthetics and security. So high-end retail shop fronts and zoo enclosures screens are often sharing the same similar aesthetic requirements of needing to be as clear as possible, but zoo enclosures are often designed to use much thicker glass. So with this in mind, we're going to explore the use of high clarity glazing in thicker glass types. And one application for this is zoo enclosure glazing. Thankfully, I'm told these images are AI generated, but it paints a picture of an extremely gloomy looking zoo. And this is basically how early zoos did used to look. But thankfully, times have changed and glass has become a key material in helping to provide a much nicer looking habitat for both the animal and the visitors, allowing for much nicer panoramic views of their environment, whilst also providing the necessary security barrier. And contrary to the last slide, the two images here have not been generated by AI and are actually projects which Pilkington have provided the glass for. And interestingly, the snow leopard project on the left is one that we'll be touching more on later in this webinar. So once again, returning to our survey, these results suggest that high light transmission is the highest priority when designing glazing for an animal habitat. 43 responses suggesting that this was the most important factor. And then that was closely followed by impact resistance and embodied carbon at 39%. So 34% of responses then suggested low reflection was of utmost importance. So we'll explore some of these properties in the next few slides. It might seem obvious, but any glazing that separates an animal from the public should be safe. So this is the #1 criteria. Not only do viewers require protection from the animal type, but the animal also requires protection from the public. Hence, any glazing should be designed as a dual purpose barrier. And of course, zoos want the paying public to be able to clearly see the animal. So the second most important criteria is usually aesthetics. So in terms of safety, first of all, we need to have a look at the type of animal for which the glazing is to separate between it and the viewing public. We need to consider the animal's potential danger level to the public, its size and weight, as well as their traits and typical behaviours. We also need to consider the animal's habitat. For example, is the glazing separating dry land to both sides, or is it water to the animal side, which would then need to consider hydrostatic loads from water pressure, as well as long-term surface corrosion, which can eventually start to obscure the glass. The size of the glazing screen and support method play a key role in the overall thickness of the glass to limit deflection when subjected to the applied loads. So for example, a 6 metre wide by 2.5 metre high glass screen would deflect much more than if the same screen was split into 3 2 metre wide panels with independent supports. Maximum capacity of people within the glazing area must be considered, and this will affect the mechanical load type to apply. And if the glazing is outdoors, it could be susceptible to temperature changes and thermal stress risks. So you may want to consider heat treated glass rather than annealed glass with any laminated glass composition. Then once the criteria is known, we can start to establish a suitable glass type in accordance with mechanical loads, impacts or temperature changes in which the glazing may be subjected to. An example of criteria can include uniform and concentrated loads, impact size and velocity, any hydrostatic loads such as water pressure, post-breakage characteristics of the proposed glass type, which is quite important in zoos. So, you know, at some point you may expect the glass to break or one of the layers to crack, but it needs to remain in situ. So that's what that is. And also thermal stresses as well, as we touched on earlier, due to quick temperature changes. In terms of aesthetics then, consideration of the lighting levels on each side of the glazing is important to understand. Ideally, the viewing public side should either be equal or darker than the animal side. Reflection and light transmission levels of a glass are key properties when considering a visually appealing screen to allow the public to successfully view the animal in its enclosure or habitat. Size and glazing method, for example, is the opening split into a number of panels, or is it fully framed, or is it structurally glazed? If there's a risk of an animal scratching the glass, then heat strengthened or toughening the glass increases the surface strength and scratch resistance. Comfort levels of the viewer should also be considered. For example, a canopy designed to protect the viewer from direct sunlight on bright sunny days and also rain on wet days is a positive design consideration. So considering these points can help create the best possible viewing experience. And other criteria can include running costs of the finished project. Typically, single glazing is chosen to allow the best viewing experience, but as we know, this type of glazing isn't energy efficient as it has a high U value. So there may be temptation then to improve the U value and switch to double or even triple glazing in some instances. But we need to consider the habitat for what it is, because once you move to insulated glass units, you can expect an increase in reflection properties as a consequence. So it's important to focus on the fundamental criteria and not try to simply tick as many boxes as possible. Budget is often a consideration, of course, meaning projects may need to consider the materials being used or specified. However, it's important to consider the breakdown of costs in relation to each component before looking to cost engineer. In the main, particularly for zoo enclosure areas, the cost of using a high quality glass specification can be relatively small in comparison to the cost of the overall building project investment, which is why it can sometimes create contractual issues when the intended specification has not been followed. You can certainly appreciate the temptation to shave a few pennies here and there, because after all, glass is glass, right? As long as clear or low iron glass is installed, things will be fine, won't they? Well, the image here shows one such example of that very problem, where a glass type was installed that was not to the design specification. The glass with the black border directly in front of you is the sample of the glass that the client required, which you can clearly see through, whereas the glass in the screen behind it is what was installed by the contractor. And as you can see, the clear laminated glass looks just like a mirror in the window, as it was not a low reflection glass. So after a few delays back and forth between the various parties in the supply chain, the glass was eventually replaced with the correct specification of Pilkington OptiView Protect. For the last few slides then, I'm going to talk about a case study for glazing enclosure which Pilkington specified and supplied the glass for earlier this year. So a recent project which was to build a habitat for 2 beautiful snow leopards at Chester Zoo, with the glazing playing a key part in the viewing experience. So back in 2022, that's how long sometimes these things take to come to fruition, but plans for Chester Zoo were drawn up to house 2 snow leopards on site. Chester Zoo then approached Pilkington UK to create a suitable glazing spec, and the spec had to be a safe partition between the snow leopards and the viewing public, and it also had to provide an exceptional viewing experience for visitors to see the new snow leopards in a custom-built habitat. So this highlights the 2 key criteria being safety followed by aesthetics. And with glazing, these types of situations, it can present challenges sometimes. So poor lighting and glass selection can make it difficult for visitors to see the animals behind the glass. And this can often then result in visitors having to lean on the glass and cup their eyes to try and spot the animal. As a consequence of that, then this can lead to fingerprints on the glass throughout the day. So unfortunately, the last visitor of the day may see quite a dirty window that they can't actually see through at all. So reflection then is a problem for glazing in zoos, and these photos are taken from a zoo, and they depict the reflection problems in a number of existing animal enclosures. And believe it or not, both these screens are glazed with standard clear transparent glass. So poor lighting and design combined with standard reflection, which is still only 8%, can create mirror reflections in bright external conditions. So how did we resolve Chester Zoo's problem then? Well, we know the glazing had to be safe and secure for purpose. It had to be low reflection and high clarity. So the product of choice was Pilkington OptiView Ultra Protect. So once we'd considered the way in which the designers wanted to split the screen up in order to fit the opening, taking into consideration the safety and mechanical loading criteria as well as superior aesthetics, we built this laminated glass specification. And note the 33mm triple laminated composition comprising 3 times 10mm heat strengthened glasses and 2 times security interlayers. Heat strengthened laminated was used to provide enhanced individual ply strength when compared to annealed glass, but also providing thermal stress resistance and most importantly post-breakage containment or rigidity in the event one or more plies were fractured, something that toughened laminated glasses cannot achieve unless they were incorporating specialist ionomer load-sharing interlayers. The Pilkington OptiView Ultra Glass is located to the outer and the inner glass plies, whilst the central glass ply doesn't need to be low reflection. So this is Pilkington OptiWhite, which is our low iron glass. This combination results in an incredible light reflection of only 1% and a light transmission of 95%, which is truly remarkable for such a thick section of glass, especially when you compare to a typical 2x4mm insulated glass unit for a domestic house, which can be anywhere between 66 and 80% light transmission. So these images show the installation of the glass on site, which comprised 2x large screens and 2 smaller viewing windows in a cave-like walkthrough experience for the viewers, providing different angles and viewpoints of the snow leopard's habitat. Each screen opening is approximately 7.5 metres wide by 2.5 metres high, and these were split into 3 glass panels supported into deep rebated perimeter frames and structurally butt jointed on the vertical joints. The final result was pretty spectacular. It opened to the public just in time for Easter school holidays this year, and the team at Chester Zoo were over the moon with it. As you can see with the message I received shortly after the installation had completed down there on the left. And the photo on the right is the one I used earlier in the slides. And we know this isn't AI generated. And why do we know this? Because our very own James Simpson on this webinar visited the zoo and got lucky and took the shot of the snow leopards walking very close to the glass during a bright sunny day. I don't even think it was a SLR camera, James, probably a mobile phone, knowing James, but it really looks good and it looks as if there's no glass there at all. So the final slide simply highlights the key collaboration of the supply chain from design concept to installation, starting with a Teams call with the design team at Chester to better understand the outline requirements of the project. This then followed with a site visit to the zoo, where a technical presentation and site survey were carried out, and then a suitable glazing specification was drawn up and proposed. Glazing samples were produced, but also we gave an outline cost plan for the proposed glass material to the appointed QS, which was helpful in making sure that everything was to budget. And then glass stock planning, which is quite important with specialist glass types, just to ensure that the specification will be available to order at the time of the scheduled installation period. And then finally, post-installation feedback with the customer, which is the zoo in this case, to ensure that the glazing achieves the desired expectation level.